Suppose we have a reaction that's not yet at equilibrium, but it's on its way. We can compare the amount of products and reactants just as if we were calculating an equilibrium constant and get a different value known as the reaction quotient, which is a number, not the same as K because we're not at equilibrium, but it gives us an indication if we're still traveling to the right or traveling to the left to achieve equilibrium. So the reaction quotient is called Q. If a reaction mixture containing both reactants and products is not at equilibrium, how can we determine in which direction it will proceed? The answer is to compare the current concentration ratios to the accepted concentration constant KEQ. Equilibrium constants can be calculated for concentrations or for partial pressures. It's done exactly the same way, but we can't call it a Kc or a Kp because the reaction is on its way to equilibrium and not there yet. But it's allowing us to predict if we're still traveling to the right or if we're back to the left in terms of comparing the number. The concentration ratio of products raised to the power of their coefficients over the reactants raised to the power of their coefficients is called the reaction quotient, called Q, the quotient. Quotient is a comparison of products over reactants. When we calculate a Q, we compare it to the equilibrium constant K. Is it larger? Do we have too much product? Is it smaller? Do we not have enough product? It allows us to figure out the direction in which the equilibrium is heading. So the reaction quotient is predicting the change direction. If Q is larger than K, the reaction will proceed fastest in the reverse direction. We want to eliminate products. Think about this: products over reactants. If the number is too big, we have too much product. We better head to the left, get rid of some of it. If Q is smaller than K, product over reactant is Q. If it's coming out too small, we don't have enough product. So we said head to the left here to use up the extra. You better head to the right and make more product. If we need that number to get bigger, we need more product so that number gets bigger on the top. If indeed you calculate and they are indeed the same, well then we are at equilibrium. If a reaction mixture just has reactants, Q is 0. If a reaction mixture is just products, Q is infinity. And that's just algebra thinking about that comparison. The reaction will only proceed in the reverse direction if it indeed is infinity. So the size of Q compared to K is going to indicate if indeed we are at equilibrium. Are we heading to the left or are we heading to the right to achieve equilibrium? If Q is smaller than K, the reaction runs to the right. The reactant is turning into product to make more product to get that equilibrium constant expression bigger. If Q is indeed equal to K, we are at equilibrium. And if Q is too big compared to K, we better use up the excess product, and it's said to head to the left where the product goes back to the reactant. Q is a number that we calculate exactly the same way. Products over reactants, coefficients become powers. We compare that number to the accepted value of equilibrium and decide if it's perfect, if it's too big, or if it's too small. So let's suppose for the reaction in which the direction is proceeding, we have partial pressure of iodine, I2, given as 0.114 atmosphere. The partial pressure of chlorine is given as 0.102 atmospheres, and the partial pressure of iodine chloride is given as 0.355 atmospheres. The reaction where iodine and chlorine combine to make ICl, this is ICl, iodine chloride. Accepted value of Kp, 81.9. Let's compare on the way to equilibrium what value we calculate for Q and then decide, is it at equilibrium, Is it going to go forward or head in a reverse direction to get at equilibrium? It's just plug and chug. Take the concentration of ICl squared, or this would be partial pressure of ICl squared, simply because of the coefficient. Set over the partial pressure with respect to iodine times the partial pressure with respect to chlorine. Plug and chug, square the top, multiply the bottom, we get 10.8. 10.8, our reaction quotient, is much smaller than the Kp, 81.9. Because it's too small, we've yet to make enough product. We need that number on top to get bigger. To get bigger, you got to point at the product. So therefore, we're going to proceed to the right, heading to make more product. For the reaction of methane with hydrogen sulfide, forming carbon disulfide and 4 hydrogens, the Kc is given for 900 degrees Celsius, and the value is 3.59. For each of the following measured concentrations, determine whether the reaction is at equilibrium, and if not, which direction is it heading. We're calculating 3 experiments. I read that wrong. 3 experiments where the quotient coming from our equation, concentration of CS2 times the concentration of hydrogen raised to the 4th power, set over the concentration of methane to the 1st power, and hydrogen sulfide squared. Products over reactants, coefficients become powers. So all they've done, one at a time, is plugged in those values and solved for Q. With experiment 1, the reaction quotient came out to be 1.24. That's smaller than the accepted 3.59. Q is smaller than K. It proceeds in the forward direction to make more product. Plug and chug in the second experiment, and we get a reaction quotient of 5.86, much larger than the accepted value of 3.59. So we got to recede backwards. We have to use the excess product, point away from that, so it's going to go left. Shifts left, shifts right is how we'll read that. And in the third trial, it came out exactly to be the Kc constant, so indeed we were at equilibrium. If Q is smaller than K, you head to the right. Making more product is the forward direction. If Q is larger than K,